And I would like to introduce the first speaker. So this is Gregory Schehr from the Sorbonne, and he's going to tell us about quantum fluctuations of 2D fermions and random matrix theory. Please, Gregory.
Okay, thank you very much, Herbert. Good morning to everybody. Let me first thank the organizers of this very nice meeting. I apologize to arrive only yesterday, but I'll be here until the end of this workshop. And today I will talk about some connections between two-dimensional non-interacting fermions and monometric theory. This is a topic actually that we started already more than 10 years ago with Satya, who is here, David Dean, and Pierre Ledoussal. And I will talk about more recent developments, which have also included collaboration with Giuseppe Del Vecchio, who is around, and Manas, who is also here. So part of the motivation for this work was this sets of experiments that were done on these quantum Fermi microscopes, where basically people are able to visualize, take pictures of Fermi gas, mostly two-dimensional, using various techniques. But this is an example of an experiment in a group of Greiner at Harvard. In fact, until recently, all these experiments were actually done using optical lattice systems, and so they were really mimicking, if you want, discrete lattice Fermi models. And they have been actually extensively used, in particular in the context of quantum simulators and for some of the topics. But it's only recently that experiments on the continuum were performed. And so this is a picture from the lab of Tariq Yefsar from that paper with his students, where they were able to really visualize Fermi 2D Fermi gas in continuum space, and I will come back to this a bit later. So to say that, just to say that this, what I will be interested in the following are mostly systems in continuous space. So the outline of my talk is like that. So I will start very briefly with to tell you or remind you the connections between free or say non-interacting fermions, I should have said, in one dimension at t equals 0 in monometric theory. And then I will come to the main two topics. So I will discuss two instances of two-dimensional systems. The first one concerns free fermions in 2 dimensions at finite temperature, and I will mainly look at the hole or emptiness probability. And I will also discuss recent experiments on that observable. And then I will then discuss non-interacting fermions in a 2D rotating trap. And this will have, you have already heard about such system during the first days of this conference. And my main purpose here will be to show you that these systems are actually connected to yet another ensemble of random matrix theory, which is the Ginebra ensemble. All right, so as I said, this work was done with these three gentlemen. Actually, it started during the PhD thesis of Riccardo Marino, who was working with Satya and Christophe Texier at that time, and together with Pier Paolo Vivo, from King's College. So that's the problem is relatively standard by now. You look at n spinless non-interacting fermions in a one-dimensional harmonic trap. And you just look at the ground state of this system. Okay, so you know that well, you will have to fill the single particle eigenstate. So you will take your first fermions and you will put it at k equal to 0, and the second fermion, etc. You will put it on k equals 1, k equal 2, etc. up to the n-1 level. And in fact, for the questions that we ask, it turns out that it's somewhat more useful to work in first quantization instead of second one. And what I want to really construct is the wave function in real space. So the ground state, which I call psi naught, is a function of this x1, x2, xn. And well, we know that we just constructed from the Slater determinant as a Slater determinant made of the single particle eigenstates, which I denote by phi k of x. And we know that they are basically these Gaussians times these Hermite polynomials. Okay. So now it turns out that this determinant here can be written in a nicer way. Indeed, well, first it's easy to see that I can just get out the Gaussian factors just using multilinearity of the determinant, and now I have to evaluate this determinant of Hermite polynomials. Okay, so let's just, as a morning gym, just do some kind of evaluating, or let's look at the evaluation of this determinant, say for n equals 3 fermions. So these are your Hermite polynomials, H0, H1, H2. Sorry, this should be H2. And so I just construct the determinant that I want to evaluate. So explicitly, this is this one. And now you see that if you just combine nicely this, say, this line with that one, well, you can get rid of the constant here. And then if you just factor out by 2 alpha here and 4 alpha squared there, well, by this simple linear combination, you end up with this determinant of monomials up to some prefactor. And this determinant is well known from standard linear algebra. This is just a van der Monde determinant, and this van der Monde determinant has this nice expression. Now it's easy to see how you can generalize it to n fermions, because you will have again this structure of polynomials of increasing degree, and so by combinations, linear combinations of the rows, well, you will get again this van der Monde determinant. So what it means is that eventually this psi 0 here up to a prefactor, which I didn't care too much about here, will be this Gaussian prefactor, which is here, times this van der Monde. Okay. Now this is psi naught. Of course, in quantum mechanics, the relevant observable will be the mod square of psi naught, and that will give you the joint probability distribution function of the positions of your fermions. If you square this guy, what you obtain is this quantity. Okay, so now if you look at it, well, you recognize, I guess that many of you, if not all of you, just recognize this object, which is just the joint distribution of the eigenvalues of random matrices belonging to the Gaussian unitary ensemble. Okay, so that's the famous GUE, and that allows you to establish a direct connection. Really, it's a one-to-one mapping between the position of fermions on the one hand and the eigenvalues of this matrix on the other hand. So in fact, many observables can be computed using this connection. I've just listed some of them here, in particular entanglement entropy in this paper by Pasquale Calabrese, Pierre Ledoussal, and Satya. We have also worked a lot on edge questions related to tracy rhythm statistics. But today I want to focus on a specific observable, which in this community has been studied a lot, which is called the sometimes emptiness probability. In the context of randometrics theory or determinantal point processes or point processes, this is usually called a Hall probability. And so in the case of one dimension, this is just the probability that you have no fermions in a given interval. Let's look at the simplest symmetric interval minus r plus r, just for simplicity. Now, why is it interesting? Well, that's one microscopic observable that sort of characterizes the properties of your gas, and in particular, that's a nice way of characterizing the rigidity of this gas. And for instance, it will be interesting to compare results that we get with the Poisson type process as a benchmark, and that's actually been very widely studied since the early work of Dyson, Mehta, Gautam, and many others. So let me just remind very quickly some basic results that we get. So now we have this connection between these 1D fermions and the randometrics theory, and there are many observables that you can just get for free. In particular, the density, which is well known in the randometrics context, and that will be given simply by the Wigner semicircle, and the typical extension will be over the square root of n. Okay, so the fermions will be essentially on a, I mean, the density will have support on an interval which is over the square root of n, and that will be given by this. This is well known in randometrics theory, but in the context of fermions, this is just a result that you can easily get using the local density approximation, or Thomas Fermi, call it as you want, kind of semi-classical one. Now, an important fact about these point processes, that means the important properties of these eigenvalues, or the positions of these fermions in 1D, is that they form a determinantal point process, which means that any correlation function, so here the endpoint correlation function, is given by a determinant. Okay. I just showed you before the one-point correlation function, which was the density, which is basically Kn at coinciding points, xx. But we know from various perspectives that such correlation function, which is this multiple integral, is given by a determinant which involves a central object, which is the kernel, Kn of xi, xj. And this Kn xy, as you know, can be constructed at 0 temperature in a very simple way in terms of the single particle eigenfunction. Okay. This, of course, holds not only for the harmonic oscillator, but for any type of Schrödinger equation, of course, or any types of fermions in a potential. So from the point of view of, say, many-body system, well, this is just, you probably have heard about this, and you know this better probably under the name of Wick's theorem, where this kernel is just given by this psi-Dagger Epps psi correlation. Okay, so that's a very important observation, because having this structure, you can eventually compute many objects, and in particular this whole probability that we are after. So now, given just let's try to understand a little bit more what happens, because of course in the large n limit, what we will need to know is how this kernel behaves in the large n limit. Okay, I mean, if you are because of this structure, the only thing that you need to know is the how this kernel behaves, and in particular in the large n limit, well, what you need to understand is how this guy behaves in the large n limit. Now, because of the structure of the density, there were actually two natural regions that emerge, depending on whether you are in the bulk, so that means close to the center, or if you are where the density is finite, or if you are close to the edge where the density is much smaller. And what you would naively expect is that when you are in the center, well, the density of particles will be higher, and so the interparticle distance will be smaller than compared to the one that you would observe at the edge, okay, where the gas is more diluted. Okay. Now, since I told you that the typical extent of the density is of order square root of n, and I have n particles, well, the interparticle distance is just square root of n divided by n, which is this 1 over square root of n. So that's quite easy to get. So that's this bulk regime. Now, at the edge, the typical distance depends a little bit more on the details. I mean, depends explicitly on the way the density vanishes close to 0. And if you do the computation correctly, what you would get is that the interparticle distance actually scales as n to the power minus 1 over 6. Okay, so which is much bigger than this 1 over square root of n. And this is where you would get the Tracy-Redan type of statistics, Airy kernel, etc. Now, although we have worked a lot on this, and I still love this physics that happens at the edge, in the following, I will actually mostly consider the case of the bulk. Okay? And in particular, in the bulk, if you look at the limiting kernel, well, it has this famous form, which is called as the sine kernel. So if you rescale the thing properly, while at the edge, as I said, you would find this Airy kernel. Now, what about the sine kernel? Well, although this one is relatively exotic, this one is relatively simple to understand because this is just in the bulk. Basically, you can just assume that your potential is roughly constant, at least on the scale of the interparticle distance. And basically, what you have there is basically the physics of free fermions. That means fermions without interaction, but without any potential. Okay, so that means that the sine kernel is exact. This is the exact kernel, if you wish, for free fermions. Okay, and that's easy to get. I mean, what you would get to do, I mean, so in this case for free fermions, the eigenfunctions are just the plane waves. And so if you compute the kernel that you would so integrate this aik x minus y on the Fermi sphere, which is here just minus kf to plus kf, where kf is the Fermi wave vector. So basically 1 over kf is the interparticle distance, okay, for those of you who are not familiar with that, but I guess most of you are physicists, so probably you have heard about Fermi wave vector. Anyway, if you just do this integral explicitly, what you would find is precisely this sign kernel. Okay, so there is no mystery behind this guy. This is just the kernel for free fermions. And that's actually the object that we want to consider here if you would like to get the whole probability, okay, so emptiness probability. Okay, so in this case, I want to compute this object. I told you, I mean, that was the main observable that I want to discuss here today. Well, because we have a determinantal point processes, so as a consequence of Wick theorem, if you want, what you can show is that this whole probability, you can write it in terms of a Fredholm determinant involving the sign kernel. Okay, so that's this object here. So Fredholm determinant, I guess most of you have heard about what it is. This is just a generalization of a determinant, but for some operator. So I want to think of this guy. This is my operator. So what it is, well, this is just the product of this k sign. So k sign of x minus y, if you want. And then on top of that, because I'm computing the whole probability, I have to insert here a projector on the region that I want to avoid. Okay, so that where the fermions are living. Okay, so in this rescaled variable, so kfr becomes this z, and so I have this simply this projector. Now the asymptotics of this guy, I mean, has been studied a lot in the 70s by many people. The first paper I think that I know is this paper by Descloiseau and Mehta from Saclay. Then it was many people actually have, including Dyson. And actually more recently, this results was nicely obtained using a relatively, I mean, handy method, this Coulomb gas method by Satya and his collaborators. And you nicely obtain this. The result of that is that in the large Z limit, what you get is this Gaussian behavior, okay, with the prefactor half here, which comes from the computation. Now, what can you get about that? Well, an interesting observation, as I said, is that you see that for Poisson point process, what you would obtain is simply an exponential times the size of your interval, which is 2 here, if you want. But so that means that you see that this decay is much faster than Poisson, and that's really a clear signature of the rigidity of your process. Okay, so that's everything is nicely understood, and you see that if you want to compute this whole probability at the end for free fermions, what you really need to compute is the whole probability for Gaussian unitary ensemble of random matrix models. Okay. Now, natural question is whether there are other potentials apart from this Gaussian unitary ensemble that are related to a random matrix theory. Now, well, it turns out that there are a few of them. In fact, all the classical ensemble of RMT can be mapped onto some fermion models. And the one that I want to discuss today, which will be useful in the following, is the one where on top of this quadratic potential, I am now adding a potential which is repulsive close to the wall and which behaves as 1 over x squared. Okay, and I will, of course, consider the case where x is positive, because basically once you're for such a potential, basically the fermions will be just trapped on this semi-infinite line. And it turns out that, as it was shown in this paper by Céline, who was a PhD student of Satya, if you look at the ground state of this model, what you end up with is not the Gaussian unitary ensemble, but another famous ensemble of random matrix theory, which is the complex Laguerre-Wishart ensemble. Okay. So we will see that this plays a very important role in the following. And as I said, in fact, there are many more than that. There are many other models which are connected to random matrix models. And well, we wrote a couple of years ago, we wrote this nice review with David Dean, Pierre Ledoussal, and Satya, which I encourage you to have a look at if you are interested. But so keep in mind that this guy here will be interesting for us, and you will see why in a minute. So what's the, so as I said, at the end, well, you may have lots of different type of models. with the different types of kernels. But eventually, in the large n limit, the number of universality classes is quite limited. So that means that, of course, for finite n, if you take different Fermion models, you will get a variety of different type of kernels. But if you start to look at the large n, well, it turns out that the limiting behaviors are very few. And there are essentially three different types of behaviors which you can already find on these two single models. Okay. So the first one is the one that we have seen before. This is just the bulk kernel, which is just the sine kernel. And this was, okay, you get it as what happens in the limit when you are in the center. But in fact, you get this kernel everywhere on that model or everywhere on that one if you are not too far from the boundaries of your system. And so that's quite universal. The other one that we have seen is what happens if you are close to what we call the soft edge. Soft edge is the edge that you would encounter in the Gaussian unitary ensemble. So if you look at what happens close to the right or to the left, or in the context of this model, you can actually compute the distribution. This will be a kind of Marchenko-Pastur. It will have a boundary here, and so finite edge, if you want, which is also a soft edge. And in these three cases here, you would get the sine kernel that we have heard about. Now, it turns out that, of course, there is a new kind of singular point here, which is what happens close to zero there. I mean, you have close to zero, you see, I mean, I can safely put this to zero, but that one, this potential will play a role, and I cannot just discard it. And it turns out that this leads to a new universality class. So that's basically the one that you would obtain for a model where you can set this to zero, so you don't feel the curvature, but you only have this 1/x squared potential. And this kernel is known as the hard edge for quite obvious reason. This is an edge that was put by hand right from the beginning, where you really forbid your fermions to live. And that actually can be written in terms of an integral of this product of two Bessel functions. Okay. And now you see that now you have actually a family of kernel, which is parameterized by the amplitude of this alpha here. So these are essentially the three main kernels that you have. We have encountered different ones if you start to look at some more exotic cases. But if you look at smooth potential, that's smooth, including this 1/x squared. That's what you would get. Now, why are they relevant? Well, we have already seen that this bulk actually plays a very important role when you look at the whole probability, say, for free fermions. Okay, so this is basically the kernel for free fermions. Now, it turns out that this guy here plays a crucial role if you want to look at free fermions, but in higher dimensions. Okay, and that's what I want to discuss now. So let's move to the d-dimensional case. Up to when this was d equals 1. Actually, there are new players now in the game, on top of the one that we have seen before. So the first one that I want to mention is Gabriel Gouraud, who was doing his PhD with Pierre and myself, who is now postdoc at CEA Grenoble, and now more recently Giuseppe Del Vecchio, who is a postdoc, sort of tunneling between LPTMS and LPENS in between Saclay and Paris. And in fact, part of the things that I want to discuss are a collaboration with the experimental group which is held by Tariq Yefsa at LKB, Laboratoire Kastler-Brossel, TNS in Paris, and his students, Maxime Dismerias, who, by the way, had his defense just yesterday afternoon. So what do we know about? So let's look at the free fermions in this case. And well, we still have determinantal point processes, right? You take free fermions, the wave functions will be again given by Slater determinants. Now, what's the kernel that you get? Well, you can compute this kernel exactly in the way that I did before. So you just integrate your plane waves, so exponential of I k x minus y. But now you really integrate over the Fermi sphere. So instead to integrate between minus kf and plus kf, you really integrate it over the sphere of radius kf. And if you do that, what you get is a generalization of the sine kernel, which is expressed in terms of Bessel functions, which has nothing to do with the Bessel kernel that I discussed before. It turns out that mathematically the same functions enter, but you see that they have not at all the same structure. In particular here, I have a kernel which is translationally invariant, and this is given by this guy. Now, if you put d equals 1, well, you can easily check that you indeed recover the sine kernel, but in general, you will obtain non-trivial functions. Okay. So what we want to do is again to compute the whole probability, but now in d dimensions. So in general, say in 2D, you would have these 3 fermions in 2 dimensions. Imagine that okay, they are bounded in this disk for some reason. But if I look at if I forget about what happens close to the edge, let me just try to understand the whole probability, which would be the probability that there is no fermions in a given domain omega. Okay, so before this was just an interval, but in higher dimensions, this can be in general any types of domains. Now, in general, this can be expressed as, again, as a d-dimensional Fredholm determinant for any types of domains. But as you can easily see, at least, even though I didn't write it, well, this Fredholm determinant is very hard to evaluate both analytically and numerically. In fact, even there have been nice methods developed in particular by Herbert's colleague in Munich, Volkmar Bornemann, to evaluate these determinants. Well, they are nicely adapted to evaluate one-dimensional situation, but in higher D, it's quite complicated. And in fact, even if we consider a sphere of radius r, where you would like to, where you have a system which not only is spherically symmetric, but the domain itself is spherically symmetric, well, it turns out to be quite complicated. So what we followed, and this is what we had done initially with Gabriel Gouraud, was to follow the development that we had started with Satya, David, and Pierre, when we were looking at the essentially some kind of extreme value questions for these d-dimensional fermions. Well, it's quite convenient because the system is spherically symmetric. It's quite convenient to go to the spherical coordinates. And basically what you will do is just to write, but then in this case, you know that your wave function, they are now indexed by a family of quantum numbers. In 3D, that would be the NLM that we know for quite some time. But what I want to say is that they typically have the structure of a purely radial part and an angular part. And this angular part is known. I mean, these are just these spherical harmonics. Okay. So I will not enter too much into the details, but just to make a connection already with what's something that we just saw before, is that this chi-NL here, so it's a solution now. So this is, I have now a one-dimensional problem where I just need to consider this radial part. And we know that this chi-NL here is itself solution of an effective Schrödinger equation, which depends on an angular number, quantum number, which is this small l here. And this fermions, if you want, these one-dimensional fermions, they live in an effective potential, which is the original one, plus a potential which is an additional one, which is this 1 over r square, which basically comes from the decomposition of this Laplacian in terms of this Casimir 1 over r square, L square. Okay, so that tells you that if you look at free fermions, V equal to 0, well, you get this model where you have just a 1 over r square potential. And as we have seen before, these fermions in such a potential 1 over r squared, well, they are described by this hard edge Bessel type of determinant. Okay? So that means that I can roughly think of this, not roughly, I can think of my d-dimensional problem as decomposed in one-dimensional sectors, each one being indexed by this angular quantum numbers L, and each of them, for free fermions, are just Bessel kernel type of fermions. Okay. In fact, if V of L is just a harmonic potential, so if V of R is an harmonic potential, there is more than that. This is really the Wishart-Laguerre ensemble. Okay, but for free fermions, you can just put V equal to 0 and you get this Bessel form. Now, the nice thing is that because your system is spherically symmetric, and the domain that we are looking at, which is we want to have the whole probability within a disk or a sphere of radius r, is also spherically symmetric. Well, these different sectors indexed by L, they are essentially independent. Okay. And as a matter of fact, using this decomposition, I will not show all the details, but effectively what happens is that if you look at this whole probability, d-dimensional whole probability, well, you can write it as a product over L. Okay, so that's this decomposition that I mentioned. So this product over the different angular sectors of what? Well, of this one-dimensional Fredholm determinant, but now evaluated for the Bessel kernel. Okay, so we had these guys, which are basically these one-dimensional systems, and that's what they are. Now, there is an additional detail here, which is that, in fact, there is some degeneracy associated to each of these L sectors, and that will produce this additional degeneracy, GD of L, which for large L behaves L to the power D minus 2, and which for D equals 2, which I will focus in a minute, is just 2. Okay. But so the main point really is that you have now decomposed your Fredholm determinant, d-dimensional Fredholm determinant, in terms of 1D Fredholm determinant of a very well-known type, because these are Fredholm determinant for Bessel functions, for the Bessel kernel, sorry, which is actually relatively well known. Now, nevertheless, getting the large Z asymptotics of these quantities, if you have played a little bit with such Fredholm determinant, well, you know that it's not a complete trivial task, but this is what we were able to do with Gabriel Gouraud. What we showed is that in D dimensions, this actually decays as exponential minus Z to the power D plus 1. Okay, so in D equals 1, this is the Z square that we have seen for the sine kernel. But more generally, you will have this exponential minus Z to the power D plus 1 with a non-trivial kappa D here, which you can express in terms of this gamma function. Good. So again, of course, for a Poisson point process, you would get exponential minus Z to the D, and that's actually something that decays, again, much faster, indicating that you have a quite rigid process. Okay. Now, the nice thing is that these properties, in principle, could be measured in experiments, and that's where we started to discuss with the group of Tariq Yefsa at École Normale, at LKB, where they have this continuous microscope that I showed you before. But the first question, of course, they asked is, say, okay, I mean, your question is, I mean, what you are doing is it's at 0 temperature, it's nice, but our experiments, they do work at finite T. Okay, so what can you do there? Well, so we had to work a little bit more, and that's what we started to do in detail with Giuseppe, well, to extend his work at finite temperature. Now, in this case, of course, working in the canonical ensemble is not very convenient, and we know that when we deal with quantum statistical mechanics, well, we usually go to the ground canonical ensemble, and the nice thing is that in the ground canonical ensemble, your process, again, becomes determinantal, with a kernel which gets modified by the Fermi factor. And that's the expression that you get. So now you again have this expression that I wrote, but the kernel that you get, of course, is a bit more complicated. So you recognize partly, I mean, this product of Bessel function that we had before, but now on top of that, you have this Fermi factor. Okay, so just forget about this. This is just exponential minus beta mu the chemical potential, and beta the inverse temperature. But here you get this Fermi factor. Okay. So that's what you need to evaluate. And again, the nice thing is that now you have only one-dimensional Bessel kernel to evaluate, and there are nice techniques to evaluate them, actually both analytically and numerically. And in particular, numerically, you can use this Bornemann method, which Giuseppe is now an expert of. So now we came back to these experimentalists, and they said, well, I mean, on our side, we are now also able to have a very precise measurements on the counting process. That means that so they are now able, you see, to produce this picture of fermions, and they may look at a given radius, a given circle of radius r, and then they can count how many fermions is there. And in this way, they can actually accumulate lots of statistics and counting the probability that they have, say, n equal to 0 fermions, which is the one that we want to compute, the whole probability, but they can also do the counting, right? What's the probability to have 1 fermions in such a disk, 2 fermions, etc., etc. And so eventually, this is what you get for a fixed temperature, which is relatively low. So TF is the Fermi temperature. So what I show here is this whole probability, so P0, the first one, as a function of the distance, KFR. So the points are the values of the experimental measurements. And the solid line is actually our theoretical predictions from this Fredholm determinant. So you see that the agreement is quite good. And in fact, you can actually go to, check other values like P1, so that's the probability that you have 1 fermions. This is also something that you can compute using this Fredholm approach. And so you see again, quite nice approach, a nice agreement, in fact, excellent agreement, and up to essentially P equal to 5, N equal to 5 they can do. So that's for fixed temperature. And now this dotted line that you see is actually the prediction for Poisson. Okay, so that would be, that's what you would get for Poisson statistics. Okay, so here the difference is not that big, but it's clearly present. You can really measure it. You see that for P1, it's even bigger. So you can actually now look at what happens as a function of temperature, just to be a little bit clearer. So this first row here, they are just the almost 0 temperature, and then you increase T. So let's look at the whole probability. This is the one that we were computing. So you see that this is basically so again, the symbols are the experiments, and the lines, the solid line, our results. Now, as you increase the temperature, you see, again, the experiments and the theoretical prediction, they again agree very well. But so you see that it starts to depart from so this one is the 0 temperature limit, and that one is the Poisson. Okay, so basically here the 0 temperature is very well matches very well. The Poisson is there, and at very high temperature, you see a crossover from the 0 temperature case to the Poisson. And again, with a quite remarkable agreement with the predictions. And this is something that you can do for the probability of having n equals 1 and equal to n equals 3. N equals 1, as you were saying, as I was saying, that the departure from Poisson is actually bigger. And so you see again a very nice crossover between Pauli exclusion principle, if you want, at 0 temperature, and the Poisson statistics that you would expect for very high temperature. Okay, so that's basically what we have done there. And let me conclude this first part by telling you that there is a very nice connections again between these fermions in general and random matrix models, and there are actually very nice structure that can be unveiled. I mentioned here whole probability spacing distribution, but there are also very nice connection with tracy rhythm, finite temperature tracy rhythm, KPZ, which I have not time to discuss here, but they are there. And then I showed you that in higher dimensions, actually, these 3 fermions are nicely related to a multiple ensemble, multiple collection of Wishart-Laguerre. And then finally, I show this quite nice crossover that we just recently published. Actually, the paper is on archive with this group of experimentalists. And that's it for this first part. Okay, so I want to move now to yet another problem. which is dealing with free fermions at 0 temperature, although we can do finite temperature. But now I want to play a little bit with my fermions. And instead of looking at them in a simple harmonic trap, I want to start to rotate this trap. Okay. You will see why people want to do that. There is a good motivation for that. People have been trying to reproduce in an artificial way. This is a nice way to reproduce artificially a magnetic field. And this can be done to reproduce essentially the quantum Hall physics that I want to discuss. So again, here there are three new people in the game. Manas, who is around, Bertrand Lacroix, Achetouane, who was doing his PhD with Satya and myself, who is now at King's College. And part of this work actually was done with Naftali Smith, who is now at the Raqqa Institute, the University of Jerusalem. So what's the problem? Well, we have already seen the 2D problem, right? Where you have just fermions in a harmonic trap. Okay, it's fine. Many things can be done. You can be, this is something that we had studied a long time back now with David, Satya, and Pierre. And as I just showed you, there is a very nice connection with a large collection of Richard-Laguerre matrix models. Okay, so it's a kind of hidden connection with random matrices, if you want. Hidden in the sense that it's not a single matrix model that is connected to it, but really an infinite family or a large family. Now, what we would like to do is to answer what happens when you start to rotate this trap. Okay, and you have heard already this kind of setup in the beginning of the week. In two talks during the beginning of this week. And so if you look at if you now look at the problem in the frame of the rotating trap, well, you have now an additional term which is quite simple to write and which couples simply to the z component of the angular momentum operator. But the nice thing is that the problem can still be solved exactly. And in fact, as I said, there is a nice analogy with a magnetic system. In fact, there are two additional terms when you start to rotate. One is just the Coriolis potential, and the other one is basically the centrifugal potential. Okay. So if you think, if you look at it, well, this is just this Coriolis potential for purely mechanical origin, if you want. Actually can be interpreted as an effective magnetic field. And in the symmetric gauge that I want to work on, A is just quite simple and simply written like that. So people really study that, in fact, mostly for bosons, but new experiments are coming for fermions, where they do simulate, I mean, they use this to simulate the effect of magnetic field. They sometimes talk about artificial magnetic field. There is a series of papers. There were very nice experiments that were carried out in a group of Jean Dalibard, for instance, a few years back. And so we want to study this problem for fermions. So you have heard about it. What happens as a function of the rotating frequency? Well, many things can be understood already on this Hamiltonian here. Well, first, this is the case of no rotation that we know. And then if you set omega, the rotating frequency, to be exactly equal to the trapping frequency, well, you have a point where you have free fermions in a magnetic field. Okay, so that means these terms are not there, and you just have the standard whole physics Hamiltonian, if you want. So these are just electrons in a plane in a magnetic field which is perpendicular to that plane. Now, of course, if you start to rotate even further, well, this centrifugal force will really win, and all your particles will just fly away. So that's not something that you want to do, because you would like still to observe them, and we want to avoid this instability, and we want to stay, as we will see, close to that guy. So close to the capital omega, close to small omega, where we recover this physics of the lowest lambda level. So I think that this problem was explained to you in the beginning of the week. Nice, I mean, the nice property is that this model actually can be solved exactly, and you can actually compute the energy levels which depend now on two quantum numbers, k and L. L couple basically to the angular momentum. So these are essentially the quantum numbers associated to the rotational symmetry, degrees of freedom. And k is more something that is related to the level of a harmonic oscillator, if you want to know. I mean, if you want to understand it. And so let me just try to understand how these levels depends on L for different values of k. So the lowest Landau level corresponds to k equal to 0. So these are these guys. So for L positive, you see a relatively mild slope, I mean, which is basically this 1 minus omega times L, which you see there. And then on the other side, they go very quickly. But now you can see what happens for the different values of k. So these are the different values of k that you can have. So these are the different Landau levels. And now you can see that if I tune correctly these levels, well, I can, now I want to have my fermions in it. So basically, if I just play well, I mean, the lowest Landau level would be only for k equal to 0. So that means that all these levels here, all the first levels will be on that branch before starting to populate the higher branches. Okay. So let's look at this limit, which then gives you a precise boundary of the value on the value of omega. And that's basically this bound that I showed you, and I'm sure you have seen it before. So omega needs to be close to the trapping frequency, but in a scale of order 1/n. Very good. So now in this case, only the lowest Landau level are occupied. And if you look at the eigenfunctions in this sector, well, they turned out to be very simple. These are just Gaussian times polynomials in Z this time. Okay, so Z is x plus Iy. But the nice thing is that now if you start to compute the ground state many-body wave function, well, it's quite easy, no? Because you don't need to you don't have any type of manipulation to do here. You have a van der Monde determinant right from the beginning, and you can just rewrite this wave function as this Gaussian factor. But now you again get this van der Monde determinant, but in terms of Z, which are I mean two-dimensional variable. Okay, so x plus Iy. So if you're a bit familiar with randometric theory, well, you see that we are very close to the ensemble, which is called this Ginniber ensemble, where if you take the square of psi naught, well, you get this guy here. And this guy is actually the joint probability density of the complex eigenvalues of the so-called complex Ginniber ensemble. So that means that you have lots of tools that are accessible. I mean, somehow this ensemble is the simplest one in randometric theory, any model that you can think of. And so that means that many computations are actually doable. And in particular, the first thing that you may think of is what is the equivalent of the Wigner semicircle. Well, here it's quite simple. This is just the density becomes uniform on a disk, which is of order square root of n, exactly square root of n. Okay, so that's what you would get from a simulation. I mean, this is very simple to find. And so you have a spatial extent in this case, which is of order square root of n. Good, so what we want to look at is our questions which we have already heard about, I guess, during the week, but also yesterday in the nice talk by Abhishek. We want to look at the number fluctuation. So I will look at a symmetric domain, which is basically the disk of radius r, which I call dr. And I am interested in the fluctuations of the number of fermions inside this disk. And I want to look at another related quantity, which is the entanglement entropy of dr with the rest of the universe. So that means here with its complementary. Okay, so that's the nice thing. Now, the very nice thing for this model, and I think this is the only one that we know, is that you can actually compute the full statistics of NR and SQ for any values of n, I guess 2, 3, 4, in terms of the eigenvalues of the overlap matrix. It turns out that because of the spherical symmetry, these eigenvalues can be computed explicitly, and they are given by this incomplete gamma function. Okay, and these are very nice objects, and you can easily get their asymptotic behaviors, and so you can get very nice and precise asymptotic results. But let me just start with some explicit results. So the cumulants of NR, so this is what I call cumulants, so this is the cumulant of order P. Well, it can be expressed in terms of a sum involving this polylog, which have as argument this lambda k or 1 of lambda k, which are these guys. It's completely explicit. Now, if you really want to have even more explicit expressions, so you would compute the second cumulant, which is the variance, but the third cumulant, and so on and so forth. So anything that you want. Now, the same actually holds for the entropy, because you know that if you know exactly the eigenvalues of the overlap matrix, well, the Rényi entanglement entropy, which is defined like this, and by analytical continuation for Q goes to 1, to get the von Neumann entropy, well, SQ will be given by this object. That's fairly explicit. So again, this is valid for n equals 2 if you want, n equals 3. So of course, the question that you are after is what happens in the limit of large n. So you see, in the limit of large n, I cannot do the full analysis for you right now because there are actually various different regimes. And in particular, you see that because you have an edge here beyond which the density is essentially 0, there will be non-trivial effects if you start to have an R, which is of order square root of n, exactly square root. So square root of n plus some fluctuations. So I will restrict myself to the case where R is strictly less than square root of n and also strictly positive. So that means that I will look at this ratio, this limit, which I call the bulk scaling limit, where R by root n is strictly between 0 and 1, and I want to look at the large n limit. So the first thing that we show, which is quite non-trivial, I think, is that, well, the cumulants, so first, they all scale like R, so you have an area law for the second cumulant, but also for the higher, etc. This somewhat can be attributed to the fact that you have a gapped system, so this might not be that surprising. But what was surprising to me, and I think to us, or at least to me, is that you see that they are in the large n limit and large R limit, they are all of the same order. So they all scale like R. Okay, so that means that the third cumulant is not negligible compared to the second one, right? So the non-Gaussianities are actually very strong in this model. And more than that, you can compute this kappa p here, I mean, as these non-trivial integrals. Now, you can do the same for the entanglement and analyze the behavior for large n. What you will obtain, again, is that in the limit of large R, of large n, keeping R by square root of n fixed, I mean, that's the proper way of saying it. This will be also proportional to R, but with a non-trivial constant, sigma q, which is this quite non-trivial integral. And for q goes to 1, it goes to a nice value, which is. Now, of course, what you would like to do, and we have discussed this yesterday a bit with Avishek, is that usually for non-interacting fermions, the claim is that there is a very simple relation between the entropy and the variance. So here, well, I mean, it's true that they both scale in the same way. So they are both of them scales like R. So that means that SQ is indeed proportional to the variance with the coefficient alpha Q, which is independent of R. But at variance with what you would expect if we had a purely Gaussian system where alpha Q would be this constant pi squared by 6 times 1 plus 1 over Q, well, what you get is that this alpha Q here is basically this non-trivial factor, sigma Q by kappa 2. So kappa 2 is simpler, it's just 1 over square root 2 pi, but the sigma Q is a non-trivial number. So for instance, for Q equals 1, the correct answer is 3.20, and okay, this is indeed slightly smaller than what you would get for the Gaussian states. So again, this case here, the violation of this equality is really a clear signature of the non-Gaussian fluctuations that you get in this model and that you can characterize fully, at least at leading order for large n. There are also very nice effects at the edge, but which I obviously don't have time to discuss. And I will just end up here by saying that, so I tried to show you this nice connection between rotating fermions and this nice ensemble of random matrix theory, which is the Geneva ensemble, which has a nice determinantal structure, a nice connection also with Coulomb gases, etc. So it's a very rich physical model. And I could show you that we can obtain exact and unusual asymptotic results for the entanglement and the full counting statistics. In fact, we can also get the large deviation function associated to the full counting statistics. I mean, many things can be done there. Now, of course, we could generalize this. We could think of at least generalizing to other types of potentials. And one that you have heard by you guys in the beginning of this week is this 1/x squared that Manas likes very much. And this ends up with this very nice wedding cake that we had found. And this with this very nice picture, I will just thank you for your attention. Thank you.
Thank you very much for a very interesting talk. Are there questions? Well, maybe I have. Okay, you asked first.
So, Gregory, in the first part of your talk, the experimental agreement, can you show the slides?
So which one?
P equal to 3. The next one.
This guy?
Yeah. So the data and the experiment are on, for example, n equal to 2, they're on top of each other.
Yes.
And those dotted lines are.
Okay. So this line here, let me try not to move. This one here is the Poisson prediction.
Right.
So this is the same as this is the dotted one that you get here.
Yeah.
And this dashed one, this one here, is the 0 temperature limit.
Okay.
And the solid line, for instance, here you see clearly, I mean, the points, they are in between the Poisson and the 0 temperature. And the solid line is really the finite temperature prediction that we have using this finite temperature Bessel kernel.
And the circles are the experiment.
Sorry?
The circles are the experiment.
Exactly. Okay. So the agreement is actually quite tough.
Okay.
Something that I should add, in fact, the theory is for non-interacting fermions, but in fact, their experiments is done in a regime where the interactions is actually non-zero. But despite of that, I mean, they are not really at the non-interacting case. They can do that using Feshbach resonance, but they are in a regime where in the BCS crossover, where the interaction is non-zero. But nevertheless, the prediction of non-interacting fermions is very good. That's probably due to the fact that the Fermi exclusion process is really sort of stronger than this type of S-wave interaction that they have.
Okay. And each time they take an image, they repeat the experiment?
Yeah, okay. So one thing that they can do is that on a given snapshot like that, they actually repeat, so they can get some statistics by simply moving this radius r to avoid some interactions, so some correlation. So this disk has to be sufficiently far from the other.
Okay.
And then they also repeat the experiments in the sense that they will reload a new gas of particles, repeat the cooling, etc., etc. So they also, so at the end, I think that they are able to make an average over typically 1,000 type of statistics.
Okay.
And the number of fermions they have is around 300 typically.
Thanks.
Okay.
Yeah, maybe just a comment. So in the part 1, these endpoint functions, correlation functions, because it's 3 fermions, as you mentioned, it's given in terms of the 2-point correlation function. And in the large N limit, the 2-point correlation, so even exactly, the 2-point correlation function is just an integral transform the Wigner phase-space distribution. And in the large N limit, the Wigner phase-space distribution, simplifies to this droplet picture.
That's
so all these kernels, they can be like the sine kernel,
right?
And the other ones, they can all be derived rather simply.
That's true. We're using yes, that's true. Yeah. This is something that we had also done. After you, decades after you. But I mean, using this Wigner approach, that's indeed. I was hesitating to talk about this because I like very much the paper we have with Satya, David, and Pierre. But time was too short.
Right. So just recently, as you mentioned in the talks by Takeshi, Ajay, and Rishikesh, so we found that the same story goes also for the 2-dimensional.
I see.
Limited context.
Okay.
So again, endpoint correlation functions can be obtained in terms of these.
The 2-dimensional, I mean 4-dimensional Wigner.
Right.
Okay,
But the 4-dimensional reduces to projects onto a
Yeah.
2-dimensional.
Sure.
Because
Because of
the lowest level comes.
Okay, thank you for your comment.
And in fact, in the next talk, this technique that originally came from string theory. Son is going to describe how it came from.
Oh, I see. Okay, interesting. Okay, great.
Okay, Deepak.
So you said that they have to redo the experiment, but can't you just time evolve the given configuration and quantum fluctuation will change the configuration with time in this experiment?
Sorry, I'm not sure I understood your question.
You said that if
they
you
reload
want to get more statistics, you have to redo the experiment again.
Yeah.
I was asking if you can just take the same experiment and just evolve in time and then you get new picture.
Yeah, I think that it's okay. There are several things that they want. The reason why they don't do that. The first one is that they are afraid of creating correlations between the two types of configurations that they would sort of average over. And the other thing is that the question is these particles, they do evolve in the continuum, but then they need to measure their positions. How do they do that? To do that, they switch suddenly periodic potential, and then using these Raman cooling techniques, they basically freeze the atoms in this harmonic, in this periodic, and then each of them will emit a photon, and so this will disturb pretty much the statistics, and then they need also to remove, this trap, etc. So the full process is very hard. That would be nice, of course, if they could do that. Yeah.
The measurement perturbs the system.
So yeah, exactly. Yeah. So which they clearly want to avoid. Yeah.
So I just have one very quick question. Geneva ensemble, I vaguely remember that people claimed that there's a transition to a Wigner crystal.
Yeah.
Is that something which you can sort of see in your analysis?
Okay, so yeah, to do that, essentially, you really need to scale the temperature, to go to very low temperature. So to scale the bit, so beta in our case is beta equals 2, because this is the integrable. But if you indeed look at the Coulomb gas with fixed beta, yes, in principle, one should do this Wigner crystal. But this is actually still under debate. There is still no precise answer to that question, which is indeed this is, pretty much what physicists have been thought about. But yeah, this is still an open question.
Okay, very good. Okay, so I think we should carry on to the next speaker. So thank you very much.
Fermion to have 0 temperature. But Landau argued that this system can be described at long distances by a classical equation. At the beginning, it must be not trivial. And from an interview of Celine, claimed that the idea of the quantum distribution function came from him. So Celine, in one of his interviews, recalled that in one encounter with Landau, in the presence of some other physicists, he said some words that Landau disliked right away, and these words are quantum distribution function. Hearing that, Landau said, quantum distribution function, there is no such thing. Then Celine said, a distribution function that depends on coordinates and momenta. And Landau said, I don't want to hear about that. Just probably because coordinates and momenta cannot be simultaneously defined for a quantum particle. But Celine persisted, saying it's a density matrix in Wigner representation. Landau still didn't want to hear about that. And at that point, one of the person who was listening to the discussion, Pomeranchuk, entered the discussion and said, Dao, that was Wigner. And that convinced Landau to listen further to Celine. And from that conversation, we have the Landau's Fermi liquid theory. Let me illustrate an example how to compute the correlation function of density, 2-point correlation function of density in using Landau's Fermi liquid theory. In order to compute the two-point function of density, we need to recall that this two-point function can be reconstructed from the linear response theory. That is, we turn on a source coupled to the density, which is the A0 component of the gauge field. That A0 leads to an electric field E, and this electric field E will lead to deviations of the distribution function from the equilibrium Fermi-Dirac distribution function. So by solving the linearized kinetic equations with an external field, fixed external field E, one can read out the two-point function of density. So it's given by a certain integral, and one can compare this integral to the result of the computation of the one-loop diagram in the free fermion theory, and it turned out that this expression exactly reproduces the one-loop diagram for fermions in the limit of small q. Moreover, nonlinear response can also be obtained by solving the kinetic equation not to linear order, but to nonlinear order. The regime of validity of this calculation is small wavelength, that is q much less than the Fermi momentum, and small frequency, omega, much less than epsilon of p. Landau's, one of the most non-trivial part of Landau's Fermi liquid theory is the way that interaction between the electrons enter. Landau's claim that if one turn on the interaction between the electrons, all that we need to modify in the low energy effective theory is to change the notion of the energy of a quasi-particles. So a quasi-particle located at the point X carrying momentum P has an energy that has a bare energy part plus a part that comes from that can be thought of as the influence of quasi-particle located at the same point, but at different momenta, P prime. And this function that parameterizes this influence is the Landau parameter. F is a function of P and P prime. The kinetic equation of this more generalized Landau's Fermi liquid theory has epsilon replaced by this epsilon of x, which appear both in the velocity and in the acceleration of in the force acting on the particles. For further convenience, to use this Landau's Fermi liquid theory further, we need to talk about one feature of the solutions to Landau Fermi liquid equation. Namely, if we start the evolution of our system with a configuration in which there is a sharp Fermi surface that separates a region in phase space where f is equal to 1 from f is equal to 0, then this sharpness of the Fermi surface is preserved under time evolution. And the reason is because the equation is basically the Liouville's equation. And we know that Liouville's equation conserves phase space volume. And that means that the region where f is equal to 1, if we follow mentally a point in phase space where f is equal to 1, over time, the value of the distribution function at that point remains equal to 1 all the time. The same with the point where f is equal to 0. And so the sharpness of the Fermi surface is preserved under the kinetic evolution. Another way to say the same thing is that if we start the evolution with this state with 0 entropy, then the evolution will preserve this condition that the entropy is 0. In other words, Landau's Fermi liquid theory can be viewed as a set of equations that describe the evolution of the shape of the Fermi surface. We can imagine a configuration with f equal to 1 or 0 as given by a codimension 1 surface in phase space. And this codimension 1 surface in phase space evolved with time. And Landau's Fermi liquid theory tells us how that surface in phase space evolves with time. The Landau's Fermi liquid theory is, we now believe that it is the correct description of interacting fermionic system in the long wavelength limit. And there are very sophisticated analysis of Feynman diagrams that show that this is true to all orders in perturbation theory. On the other hand, as formulated by Landau, Landau's Fermi liquid theory is not a field theory. It's not something that is given by an effective action or a Lagrangian. Instead, Landau's Fermi liquid theory is formulated through an equation of motion, the kinetic equation. So we don't have access to a large toolbox of effective field theory. We don't get insight from the Wilsonian viewpoint. So these why we want an effective field theory description of the Fermi liquid theory. And one of the reasons is that this field formulation might be important for the problem of non-Fermi liquid, where we have to couple the Fermi liquid theory to a gauge field. We could, for example, we might be tempted to perform a Wilsonian renormalization group on that system. And without knowing how to write down an action describing the Fermi liquid, we would not be able to do the integration of the high energy degrees of freedom. So this issue with Landau's Fermi liquid theory is well known, and there have been many previous approaches trying to reformulate Landau's Fermi liquid theory as an effective field theory. And these approaches can be roughly subdivided into 2 categories. In the first category, one tried to formulate an effective field theory of the fermionic quasi-particles, the Landau's quasi-particles, that are near the Fermi surface. And this approach was pioneered by Benfato, Galavotti, Shankar, and Polchinski. One of the complications in this formulation is the existence of the Fermi surface. And that leads to the necessity of doing very non-trivial scaling of the momentum of this quasi-particle. When we do Wilsonian renormalization group, we have to integrate out degrees of freedom and leave out a thin shell near the Fermi surface. And there is the scaling of the momentum near this Fermi surface becomes quite intricate. It's also quite non-trivial to show that Landau's parameter gives marginal interaction. That is, and beside Landau parameter, nothing else besides Landau parameters and the Cooper pair interaction. There is no marginal or relevant interaction. In fact, it's even more difficult to show that Landau's parameter give us the exactly marginal interaction, as we know from Landau's Fermi liquid theory. A second set of approaches is based on the idea of bosonization. It is very elegant in 1+1 dimensions, where one can map the fermionic field to a bosonic field. But the bosonization becomes very clumsy in higher dimension. And there are various technical difficulties that is usually associated with the word patches or curvature of the Fermi surface. And the one technical difficulty is that we get an infinite number of bosons. So in this talk, I'm going to restrict myself to a very concrete problem. I'm trying to answer a concrete question, whether one can reformulate Landau-Fermi liquid theory as a field theory formulated in terms of a certain action S that depends on certain field phi, so that the condition that the action is extremized with respect to phi, that is ds, delta S over delta phi is equal to 0, give us Landau's kinetic equation. I will try to convince you that the answer is yes, and the method that one can use to write down this action is the method of co-adjoint orbit. This method of co-adjoint orbit has been applied to non-relativistic fermions in 1+1 dimension. And here I'm going to try to do that same thing in dimension larger than 1+1. The main idea is that in order to parameterize the state of a fermionic system with a sharp Fermi surface, it's most convenient to view that state as the result of applying a canonical transformation on the original, say, ground state of the system. A state with a sharp Fermi surface can be obtained from a reference state by a canonical transformation. This canonical transformation acts in the phase space of a single particle. So before proceeding, let me give you a short mathematical interlude on the mathematical notion of the co-adjoint orbit. A lot of that may be familiar to many people in the audience. But let me recall the notion of the adjoint and co-adjoint representation. Consider a Lie group that I call here G. The corresponding Lie algebra is also denoted by the Gothic letter G. If I take elements of the Lie algebra, I can exponentiate it and get the element of the Lie group. The adjoint representation of the Lie algebra is that each of the member of the Lie algebra is put in correspondence with a linear map acting on the Lie algebra itself, that map any member of the Lie algebra to the commutator of G with F. So clearly, this is a linear representation. That is, we map elements of the Lie algebra to a matrix acting on the space of the Lie algebra. And exponentiating the adjoint representation in the Lie algebra, one can get the adjoint representation of the elements of the Lie group. So I am sometimes use a mathematically correct notation at U times F, but sometimes I will use the physical notation where the action of the element of the Lie algebra of the Lie group on the member of the Lie algebra F is denoted as U F U minus 1. To define the co-adjoint representation, we introduce the notion of the dual space. The dual space is a linear space, G star, where we can define a scalar product between any vector in dual space and a member of the Lie algebra. Convenient way to think about this scalar product is to associate capital F in the Lie algebra with the upper index and the lowercase f in the dual space with the lower index A. The co-adjoint representation is defined uniquely in such a way that if I take two elements, two objects, one the elements in the dual space, another is the element of the Lie algebra, and then act on elements of the Lie group on both capital F and small f using the adjoint and co-adjoint representation, the scalar product does not change. So that defined how the co-adjoint representation have to act in the dual space. And the last notion is the co-adjoint orbit. The co-adjoint orbit, if I take a reference vector in the dual space and then transform it using all possible members of the Lie group, and then we get the so-called co-adjoint orbit. So this co-adjoint orbit by construction is the coset, a coset of the full Lie group and the subgroup that leaves this F0 invariant, or the stabilizer subgroup of the F0. So one simple example is the SU2 group. So the SU2 algebra can be viewed as a three-dimensional space, F1, F2, F3. And the dual space is also a three-dimensional space. We can define the scalar product to just be the scalar F1, the usual scalar product between the two vector F and capital F. Both the adjoint and the co-adjoint action is just the rotation in three-dimensional space. And the co-adjoint orbit is just a sphere. So in this example, we see almost no distinction between the adjoint and co-adjoint representation. But in our case, with the physics of the Fermi surface, we find it still convenient to make this distinction. And the reason is the following. So if we recall, let me first talk about the group first of that we are going to consider, the group of canonical transformation. An infinitesimal canonical transformation is given as a transformation in phase space, x and p going to x prime p prime equal to this expression here. Here you recognize that it is just a Hamiltonian evolution with the function f being the Hamiltonian during a time that is very small, epsilon. And the consequence of this, we know that Hamiltonian evolution preserves Poisson brackets. And so the Poisson bracket between x prime p prime is the same as Poisson bracket between x and p. So all these infinitesimal canonical transformation form a Lie algebra. The commutator of two elements of the Lie algebra is again canonical transform, an infinitesimal canonical transformation, but now given by a new function which turn out to be the Poisson bracket of the function f and g. So this expression defines the structure constant of our Lie algebra. All elements of the Lie algebra are functions of x and p, and here is how the commutation relation is defined. And the Lie group is simply the group of finite canonical transformation. That is time evolution, not during an infinitesimal time, but during, say, unit time. Then we denote this finite canonical transformation as e to the power of f. Now, the dual space, the Lie algebra is given by function in phase space. We are going to take the dual space to be also the space of all functions of x and p, and define the scalar products to be integral over the phase space of the product of function f and small f and big F. The reason why we are making a distinction between the dual space and the Lie algebra, despite the fact that both are parameterized by function in phase space, is that we want to associate these spaces with different physical quantities. The algebra, this function f, we are going to associate the notion of physical observables. For example, if f is equal p squared over 2m, that observable is the kinetic energy. And we want to associate the notion, this small f, the member of the dual space, with the distribution function. And the scalar products of small f with big F is going to be interpreted as the average of the observable capital F in the state given by the small f. That scalar product is the classical analogs of the quantum mechanical quantity, usually written as a trace of f hat times a capital F hat. So that f hat is the density matrix, and this quantity is the average value of the operator f, capital F, in a state given by the density matrix, small f. The adjoint and co-adjoint group action is can be worked out. For example, if I have u, that is an exponent of a function g, of elements of the Lie algebra given by a function g, then acting u on a function f just give us a Taylor expansion where every term is just another Poisson brackets of the function g with whatever we have here. One can show that this preserves the scalar product. Now we can try to understand the notion of co-adjoint orbit. Let's take the reference state to be the state of the that we would usually associate with the ground state of isotropically invariant Fermi gas. So the reference state has occupation number or distribution function F0, which is just a theta function that is 1 inside a Fermi surface and 0 outside. And that distribution function does not depend on x. To find the co-adjoint orbit, we act on this distribution function, all possible members of the group of canonical transformation. But canonical transformation is, we remember, it's just a Hamiltonian evolution, and that preserves the sharpness of the Fermi surface. So a state with a sharp Fermi surface remains after the transformation, the Fermi surface remains sharp, and the number of particles is not changed. But we can show that any small perturbation of the Fermi surface, at least all the small perturbation of the Fermi surface, can be obtained by using a canonical transformation. So in this way, a state of a Fermi liquid is a point on the coadjoint orbit. And our task is to parameterize the coadjoint orbit and then write down the action. So the coadjoint orbit clearly is a coset. It's parameterized by a member of the coset which is the coset G over H, where G is all the canonical transformation, and H is a group of canonical transformation that preserve the reference state, preserve the ground state of the fermionic system. Let's see how it works near the unity, that is for small perturbation. Consider a group elements in the group of canonical transformation in the form exponents of -phi, where phi is a member of the Lie algebra that correspond to a function phi that is much smaller than 1. Then working out the action, the coadjoint action, we find that after the canonical transformation, the Fermi surface got deformed. It's no longer a round Fermi surface, but there is a deviation that comes to be proportional to p hat times gradient of phi. P hat is the direction of the momentum p. So if the green curve, if the red curve here is the ground state, then the green curve is after the action. There is an ambiguity. We can replace U by U times V, where V is an element of the stabilizer group of the ground state. And that ambiguity can be used to do a gauge fixing. And the gauge fixing we can do different kind of gauge fixing, but one way to gauge fix is to require this function phi to be not a function of x and p, but a function that does not depend on the magnitude of p, but depends only on the direction of p. In 2 dimensions, that direction of p is parameterized by a single angle theta. So here we see the appearance of an infinite number of scalar field. Each scalar field, so roughly 1 scalar field per angle, or 1 scalar field per point on the Fermi surface. So the action can be written in the following way. I'm going to write down an action and then show that this action under variation give us the Landau's equations, kinetic equation. So the action has 2 parts. There is a part that I call Wessuminer-Witten or Berry phase part, and the second part is the Hamiltonian. So the first part is the following. So we need to find this first part. It has one derivative with respect to time, and so one can think about that as a Berry phase part of the action. U is the element of the Lie group that correspond to the state of the fermionic system. Remember that the state of the fermionic system is described by a shape of the Fermi surface. Any shape of any Fermi surface with a given shape, assuming certain topological and smoothness condition, can be obtained from the original Fermi surface by acting on it a canonical transformation U. So here U is the canonical transformation. Clearly it depends on time because the system evolved with time. u minus 1 dtu is an element of the Lie algebra. And so there is one can take the scale of this quantity, it makes sense, the scalar product of F0 with this element of the Lie algebra. And then the second term is just the Hamiltonian. For free fermion, the Hamiltonian is just the scalar product of F with the kinetic energy of the fermion. Say for non-relativistic fermion, that could be p squared over 2m, but it doesn't have to be p squared over 2m. By using the properties of the invariance of the scalar product under adjoint co-adjoint action, one can rewrite this as F0 scalar product of F0 with u minus 1 epsilon u. That form turned out to be rather convenient for calculation. The Wesson-Witten term can be alternatively written as a two-dimensional integral of something called the Kirillov form or Kirillov-Kostanz-Suryo symplectic 2 form. It is one of the very important notions in the mathematical theory of the co-adjoint orbit. So this KKS symplectic form has the precise definition like this, a formal definition that is usually encountered in textbook. So consider the co-adjoint orbit. Imagine that as a manifold, and F is some point on that manifold. Symplectic 2 form is a map between two tangential vector, delta F1 and delta F2, to a number. So the definition of that 2 form is that it maps delta F1, delta F2 into this quantity. So let me explain. Each of these tangent vector can be thought of as can be parameterized by an element of the Lie algebra that generate infinitesimal transformation from F, say, to F plus delta F1. And by taking the commutator between two elements of this Lie algebra that generate these two vectors with the vector F, which is now in dual space, we find the formal definition of the symplectic 2 form. It's now a non-trivial task to show that this symplectic 2 form does not depend on the choice of the elements of the Lie algebra that generate this vector delta F1 and delta F2. There is a certain ambiguity, but this scalar product does not depend on this choice. And moreover, this symplectic 2 form is closed. So if you go back to this action, the first term looks like simply is the type of PQ dot term in quantum mechanics. And this H is the Hamiltonian. So the Hamiltonian, this Hamiltonian, if we know properties of, if we know the Hamiltonian, in order to know the Hamiltonian, we need to know the dispersion relation of the particles. We will need to know the Landau parameter to know how the Hamiltonian depends on the shape of the Fermi surface. But the Berry phase is a universal quantity. It does not depend on the, it is a rather kinematic, it has a rather kinematic origin. And one can think about this term as a Berry phase at that one obtains, the system acquires when the Fermi surface changes its shape. And the Berry phase term is universal for Fermi liquids. So we can, I'm not sure if I have this slide here, but By differentiating S with respect to the field phi, one can convince ourselves that one get the Landau's kinetic equation. One can also expand the Lagrangian, the action to second order in field phi to get the quadratic action. And from this quadratic action, one can compute various things. For example, so here let's look at the quadratic action. It's basically action that is a linear superposition of action for chiral boson. We have one chiral boson per point on the Fermi surface. At each theta, we have one chiral boson. And the density of the system, the density of the fluid of the fermionic system is just the sum of the density of each of these chiral bosons. And we can compute the two-point correlation function of the of our fermionic system in the fermionic language that correspond to integrating out the fermion in this loop. But in the bosonic language that we are working with here, we map the problem into evaluation of a tree diagram where each of these is a vertex, and there is just one propagator of phi running inside. And doing the calculation, one can convince oneself that we reproduce the two-point function of the free fermionic system. We can also go further in power of phi. Each of the term, the Wetzel-Witten or the Berry phase term or the Hamiltonian term would contain, would give rise to various cubic term in phi. So here, what is important is that we now see that the especially from the Wetzel-Witten term, the phi with at different point on the Fermi surface start to couple to each other. And we can compute three-point function for fermion using this Lagrangian and convince ourselves that our calculation in the bosonic theory, where the three-point function calculation reduces to evaluations of certain tree-level diagrams, reproduces the loop calculation in fermionic theory. Moreover, the bosonic theory is more natural in a certain sense, that if we take the momenta and frequency of the external legs goes to zero, then each of these fermionic diagram behaves like 1 over q, but their sum is q to the 0. So there is subtle cancellation between two fermionic diagram where the fermionic loop goes in two opposite directions. But in the bosonic language, that each of the diagram has the natural size, q to the 0. There is no cancellation needed in order to evaluate the three-point function at low momentum. The Landau parameter enters the theory as a term that mixes the chiral boson at different angle, at different point in the Fermi surface. So here's this F theta and theta prime is the Landau parameter. By construction in our bosonic description, Landau parameters enters the quadratic action. It's just different from the usual quadratic action in the sense that it's coupled by a different point in theta. Since it's part of the quadratic action, the Landau parameter is exactly marginal. And this is a fact that is actually very non-trivial to see in other approaches. Here, in this bosonic approach, it's just rather trivial. One can also convince ourselves that interaction term, phi cube, etc., are irrelevant in Fermi liquid theory. we can try to extend the theory by including other degrees of freedom. Before doing that, let us recall that this the algebra of canonical transformation can be viewed as the classical or long wavelength limit of the algebra formed by fermion bilinear, psi decker x, psi y, or written in a more symmetric form. In this way, this operator, one can check, form a closed algebra if psi is if psi satisfies the usual anti-commutation relation of a fermionic field. So this tells us how to extend the theory to spinful Fermi surface. We need to extend the algebra to include operators that are not diagonal in the spin space, or we can extend the theory to BCS theory to include the BCS correlation. We need to extend the algebra to include not only psi decker psi field, but also the field that looks like psi x, psi y as charge -2 or charge +2. So let me go to the conclusion. The method of coadjoint orbit provides a rather natural way to write down an effective field theory of a Fermi liquid. It leads to a bosonized formulation of the Fermi liquid in terms of an infinite number of bosonic fields. Using this theory, one can reproduce a linear or nonlinear response of a Fermi liquid. An open problem is to compute. We haven't investigated this question fully. How to compute non-analytic? Can we use this theory to compute non-analytic correction to Fermi liquid theory that presumably arises from loop diagrams in the bosonic theory? All the calculations that we have done so far are tree-level calculation. But there are loop diagrams that should contribute to non-analytic behavior of Fermi liquid. By doing power counting argument, we can see these corrections appearing. Perhaps this theory is this formulation of Fermi liquid theory is a suitable starting point for the study of non-Fermi liquids. And I think we still have a lot of work to do in this direction. Thank you very much.
Thank you very much. Thank you very much for this most interesting presentation. So are there questions? Yes, please.
Hi, Son, can you hear me?
Yes.
Yeah, that was a fantastic talk. Thanks a lot. So I just wanted to make one point that in our work that you mentioned, we could derive this coadjoint orbit action starting from the fermion path integral in case of the non-interacting fermions by changing variables to the from the fermions to the fermion bilinears, etc. Which we could do only for the non-interacting fermions and in 1+1 dimension. And later we could generalize that also to ON fermions, which were basically describable by mean field, like Cross-Nebo kind of system. But my question to you is that, is there a possible derivation of the coadjoint orbit action in case of the, the interacting theory with the Landau parameters and so on that you have? I mean, I see what you are doing, but I'm saying that is it possible to start from a fermion path integral with the interactions and make change of variables and arrive at your action?
Let me first answer your question, but not directly. So in 1+1 dimension, one can bosonize fermion with non-linear dispersion. Say, for example, free fermions, but with quadratic dispersion relation. And in 1+1 dimension, actually, one can compare the result of this coadjoint orbit with previous in what first dimension one can do bosonization in different another.
Yeah, but I'm not talking about
Okay.
bosonization in terms of the collective field, like the density variable and so on. I'm talking about bosonization in terms of this, the Wigner distribution quantity.
Right.
Yeah. So from like psi x to rho xp, that bosonization. So that could be exactly done through a change of variables in the path integral with constraints. So it becomes like a constraint path integral in terms of the Wigner distribution with the constraints like, the u star u equal to u and the integral of, the rho star rho equal to rho. But this rho is the phase space density. And the integral of rho is equal to n as delta functions appearing in the path integral measure. And then the, the action formulation for that variable has the Kirillov, term in the action. So it's probably not in the paper that you mentioned here, but in the following paper we had a proof of this bosonization. Yeah.
We were not able to derive to go through the road that you outlined in higher dimension, but it might exist such a derivation.
I see.
Any other question? Well, so that doesn't seem to be the case. So thank you very much for this presentation. And thank you to all the speakers, to the two speakers of this morning. Okay, so we adjourn at 12 o'clock and there will be the discussion session.
Bye.
Thanks a lot, Son.